The name of the module is Multicollinearity Remedies Part 1. Multicollinearity is a very important assumption of linear models. When we assume multicollinearity, we usually make the assumption that multicollinearity is absent. In case multicollinearity is present, under those circumstances, we have one or more predictors which are correlated to one another. And because of this reason, when we fit a linear model using the predictors which are correlated, we get faulty results for the estimates of the parameters and other inferential procedures. So what we do is we try to detect multicollinearity, and once we are sure of its existence, we would like to remedy the situation and then fit a linear model to our data set. In this module, we will look at different methods to remedy the situation where we have multicollinearity present in the data. Multicollinearity is a situation where there is very high intercorrelation between predictor variables in a regression setup. Multicollinearity, if present in data, poses a serious threat to the estimation and inference about the regression parameters. It makes the variances of the parameter estimates very high, and thus the coefficient estimates become very difficult to interpret. Also, while testing the regression parameters, we end up with a very small value of the t statistic, which is given by the estimate of the parameter and divided by the standard error. And because standard error is very high, it gives us a very small value for the t-test statistic. But do we need to take care of multicollinearity? The symptoms of multicollinearities are such that they can make choosing the correct set of predictor variables for the model more difficult. For instance, if we have 5 predictor variables in a regression model, out of which 2 of them are highly collinear, which means 2 of them have a very high correlation coefficient, and a third which has a medium amount of correlation coefficient with the other 2. In that case, it makes it difficult to keep the one predictor that is relevant for the model and then remove the ones that are redundant. It also makes difficult to interpret the precise effect of each predictor variable. Like I have mentioned before, since in case of multicollinearity there are more than one or more than 2 predictor variables which are collinear, then the effect of each of these collinear predictors are more or less same on the response variable. In such cases, the interpretation of the corresponding regression coefficient becomes very difficult. However, multicollinearity does not affect the overall fit of the model. When we test the overall fit of a multiple regression model using the f-test statistic, it is not much affected by the presence of multicollinearity, and the parameter estimates under multicollinearity are still unbiased, although they are now inefficient and not blue anymore. In this module, we will discuss several methods to remedy multicollinearity. Some of them are respecification of the model that we have considered to fit to our data. We need to respecify the model in order to include the variables which are not multicollinear and remove the redundant ones. We can also use additional data or collect more raw data in order to fit into the regression model. We can also use independent estimation method for the parameters. We can use the method of prior restrictions placed on the regression parameters. And the last 2 different methods of remedying multicollinearity which have become very popular over time are principal component regression and ridge regression technique. In this module, we will discuss some of these methods, and the remaining will be discussed in a follow-up module. Let us look at the first method of remedying multicollinearity from a data set. The first method is model respecification. Multicollinearity in most cases is caused by the high correlation between 2 predictors, and in such situations a possible remedy could be restructuring the predictors. For example, if we are trying to fit a multiple regression model with 3 independent variables x1, x2 and x3, and suppose these 3 variables are nearly linearly related to each other, then for a researcher it might be possible to find a function of these predictors, an appropriate function that can be used such that x equals x1 plus x2 divided by x3, or x equals x1 times x2 times x3, such that the information about the 3 predictors are preserved and also multicollinearity is reduced because we have put the 3 predictor variables in one function. Now, another popularly used method of model respecification is variable elimination. This is a very obvious method of removing multicollinearity from a data set. Suppose we have the same 3 regression parameters, the 3 regression predictor variables x1, x2 and x3, and we know that they are collinear. Then just keeping one predictor variable in the model and removing the other 2 which are collinear with the first one is one of the choice for removing multicollinearity. In the previous slide we have talked about defining a function of the collinear variables. So we can also think of removal of variables that have high correlation with the other predictors. This method is usually very effective. However, removal of predictor may also indicate that the predictive power of the model has been compromised. When we collect data on several predictor variables, we gather information. So even if the variables are intercorrelated, they carry some amount of information about our response. So removing any one of them from the model due to the presence of multicollinearity would result in loss of information. Another method of removing multicollinearity from a data set could be use of additional data or by collecting more data. Now, while discussing consequences of multicollinearity, we have seen how multicollinearity is a sampling phenomena. Suppose we have a population and we have drawn data from a small sample from the same population. Now, it could be so that only for that particular sample the values of the predictor variables are such that they represent a collinearity between the predictors. However, if we select a different sample, then the data collected for the predictor variables for that particular sample could be values are such that there is no multicollinearity. So, including more data, that is increasing the sample size, is a good option for removing multicollinearity. Since the standard deviation of the parameter is a function of sample size, increasing the sample size will decrease the standard deviation, which means the more sample data we have, the less is the deviation of the data from the actual values from the population. But collecting additional data is not always possible because there is time constraint and cost constraints in case of studies. A third method that we can use to remove multicollinearity is the independent estimation of one or more of the parameters corresponding to the collinear predictors. So, in this case, let us consider the Ando-Modigliani consumption equation, which is given by Ct equals beta naught plus beta 1 yt plus beta 2 wt plus ut, where Ct is our response variable and the 2 predictor variables are yt and wt. For the given case, we can obtain the estimate of the parameter beta 1 corresponding to yt by beta 1 hat. Then the above model can be restructured and rewritten as Ct minus beta 1 hat yt equals beta naught plus beta 2 wt plus ut. So, this now becomes our new model, where the left hand side is now known because we have inserted the estimate of beta 1 instead of the unknown parameter beta 1, and on the other hand, On the right side, we have only one predictor variable, beta naught plus beta 2 Wt plus Ut, where Ut is the error term. So thus treating beta 1 hat as known value will help us in estimating beta 2 more precisely. And to handle such problem, we use the mixed estimation approach. Now let us move on to the principal component regression method of removing multicollinearity from a data set. This is one of the more extensive and more intense and sophisticated method of removing multicollinearity, and there is a lot of maths involved in finding the estimates of the regression parameters using the principal component regression. And in the following few slides, we will discuss the principal component regression method in detail and see how we can find the estimates of the corresponding parameters. So in principal component regression, it is a technique employed to fit multiple regression model when the assumption of multicollinearity is violated. In case of multicollinearity, although the parameter estimates are unbiased, their standard deviations become very high. In principal component regression, we add a degree of bias to the regression coefficient estimates and achieve a lower standard deviation. So the bottom line here is to compromise the biasness of the regression coefficient to achieve a lower standard deviation. Now consider a multiple regression equation given by y equals x times beta plus epsilon, where y is the dependent variable and x represents the independent variables matrix and beta is the regression coefficient vector which we wish to estimate, and epsilon represents the error terms. The first step in the principal component regression is to standardize the independent and dependent variables by subtracting their corresponding means and dividing by the standard deviation. So for the principal component regression model, let us consider the multiple regression equation in the matrix form. The model is written as y equals x beta plus epsilon, where y is the vector of response variable, x is the matrix made up of the predictor variables, and beta is the regression coefficient that we wish to estimate, and epsilon represents the error terms. The first step in principal component regression is to standardize the independent and dependent variables by subtracting their corresponding means and dividing by the standard deviation. So when we have data on our response or dependent variable and the data on the predictor variables, for each of them we find the mean and the standard deviation, and then standardize each of the dependent and independent variables by subtracting from them their mean and dividing the difference by the standard deviation. And the remaining stages of the analysis are performed using these standardized variables. So for the rest of the process, we use these standardized values and we obtain the estimates of the parameters, and finally when we obtain the regression coefficient estimates, we adjust them back to their original scale. So in case of ordinary least square estimation of the parameter estimates, we had seen that the regression coefficients are estimated using the following formula, and the formula takes the form beta hat equals x prime x whole inverse x prime y. Since we had standardized variables, x prime x equals r, where r is the correlation matrix of the predictor variables. If you remember, the correlation coefficient is given by covariance between two variables divided by the standard deviation of the two variables. So since we have standardized our predictors and independent variables, we now have for the different predictors the predictor minus the mean divided by standard deviation, and since we are using this form of the predictors, x prime x, which is the matrix of the standardized predictor variables, they equal R, which is the matrix of correlation. So in order to perform principal component regression, we transform the predictor variables to their principal components. So let us look at the mathematical form. X prime x, this matrix can be written as a decomposition using three different matrices P D times P prime, where P is the matrix of eigenvectors of x prime x and D is a diagonal matrix where the diagonal elements are lambda 1, lambda 2, lambda p, which are the eigenvalues of the predictor variable matrix, which is x prime x. So, we can write the regression model in terms of diagonal matrix D and the eigenvector matrix P by replacing x prime x by P D P prime. So, we have the regression model in terms of x, p and d of the following form: y equals x times p prime beta plus epsilon, and as we know that p is the matrix made up of the eigenvectors of x prime x, p is an orthogonal matrix, so p times p prime equals identity matrix I. Since we have y equals x p times p prime beta plus epsilon, this can be written in terms of z, which equals y equals z times alpha plus epsilon, where z equals x times p and alpha equals p prime times beta. So, as you can see, the matrix x and the vector of so the matrix z equals x times p is a transformation of our matrix of predictor variables x, and alpha is a vector of regression coefficients, which is a transformation of the original vector of regression coefficients beta. So, z prime z we can see gives us p prime x prime times x times p, which equals p prime p d p prime p, which equals the matrix D. The columns of the matrix Z, which equals z1, z2, zp, are a new set of predictor variables, and these are nothing but the principal components of x1, x2, xp. So, now based on the restructured model that we have seen, where y equals z times alpha plus epsilon, we now wish to estimate the vector of parameters alpha. The least square estimate of the parameters alpha is given by alpha hat equals z prime z whole inverse z prime y, where z prime z can be written as d. So, alpha hat equals d inverse times z prime y, and the covariance matrix of alpha is given by variance of alpha hat equals sigma square times z prime z whole inverse equals sigma square times d inverse. So, since the diagonal elements of the matrix D represent the eigenvalues of x prime x, it means smaller eigenvalues will imply higher variance of the corresponding regression coefficients. Let lambda j refer to the variance of the jth principal component. In that case, if all lambda j equals 1, then the predictors are orthogonal, and if all lambda I equals 0, then the predictors are perfectly linearly related. In case where 1 or more lambda j equals 0, it implies multicollinearity is present. The underlying idea of a principal component regression approach is to combat multicollinearity using less than the entire set of principal components for the model. As we have seen, in principal component regression, we had started with standardizing our dependent and independent variable, and we had then transformed the matrix of predictor variables, and now we obtained the principal components of x prime x, and based on the eigenvalues we retain the certain principal components which are significant statistically and remove the others. So, here in removing the principal components, we are removing multicollinearity from the data set. So, in order to obtain the principal component estimators, we arrange the predictors in decreasing order of eigenvalues. Lambda 1 greater than equals lambda 2 greater than equals lambda p, and all of them are greater than 0. And if you remember, in principal component analysis, the rule of thumb of selecting the significant principal component was by looking at the eigenvalues. The ones which had eigenvalue 1 or more were retained and the others were removed. So if the last S eigenvalues are very close to 0, we remove those S principal components of the predictor variable matrix from the model, and the method of least square is then applied to the remaining components, and we obtain the estimates of the parameters. So in principal component, the regression coefficients are reduced to the S predictors retained based on the eigenvalues. The vector of regression parameter is then written as alpha hat subscript PC representing principal component, which then equals beta times alpha hat, where beta equals beta 1 beta 2 beta p, and in this vector we have the first p minus 1 components equal 1 and all the others are 0. And let me remind the reader, this vector beta is not the same as the vector of regression coefficients that we started with in the regression model. So thus the principal component estimator for the model is given by alpha hat PC, which equals alpha 1 hat, alpha 2 hat, alpha p minus S hat, and all the remaining components are 0. So this was the theory behind principal component regression model. This kind of models can be fitted using the PLS function in R. We can also use the PCR function to perform principal component regression. We will dedicate a separate module to the discussion of the use of R in removing multicollinearity using principal component regression model. In this module, we have seen how we can detect multicollinearity and remedy the situation when multicollinearity is present in the data. In a previous module, we have seen the serious consequences of the presence of multicollinearity. So, statisticians have developed several different methods of remedying the situation in the presence of multicollinearity. We have learnt in this module different methods, namely the principal component method of remedying the situation when multicollinearity is present, and we have looked at the details and the mathematics behind this model, and we have also discussed a couple of more methods of remedying multicollinearity, but they are not as extensive as the principal component method. In a future module, we will discuss how we can use a data set and use our software to remedy multicollinearity from a data set using the principal component regression method.